Good evening, everyone. Welcome to the NPTEL session third. So, I am Umar Rashid. I work as a PhD student in Indian Institute of Science, Bangalore. So, I'll be helping you with solution of some of the questions, and also in the meanwhile or in the process I'll be explaining some of the concepts that are required, fundamental concepts that are required in order to solve those questions. Okay, so today we'll solve some of the questions that are related to the dipole moment, and then we'll go on solving some of the questions that are related to the fluid dynamics. That means when a fluid moves from one place to another. Uh, so in the meanwhile, let us start. The first I'll give a brief overview of what I'll be doing in these. So from in the last semester, in the last session, we have solved till 5. Now today I'll be solving question number 6, question number 7, 8, 9, and 10. That is, these questions are related to the dipole moments, and then after that I'll be solving and after that we'll start the other questions that are actually related to the fluid dynamics that I have shown, and we'll be discussing viscosity and other things. And in the meanwhile, I'll be giving a BF overview or revise some of the fundamentals that are related to the heat transfer, the heat conduction, similarly different ways of heat transfer, conduction, convection, and some of the day-to-day activities that in which we see the heat conduction or the convection in the process. And then thermal conductivity, the various equations in which we can calculate the thermal conductivity, the various laws in which this thermal conductivity can be calculated from a system. Similarly, then I will go with the Widman-Franz law, and then the closely related concept that is actually used in gases is the mean free path, and various equations of the mean free path I'll be deriving. Then the average velocity, then diffusion. So I'll give a brief overview of the diffusion and how the diffusion can be calculated. Then what is the concept of mean square deviation, laminar flow, similarly the viscosity and the various viscosity relations. Then how we can quantify the viscosity in a pipe, or whether in a laminar flow, and how it affects it. Then we'll be calculating the speed in the right. Then similarly the Stokes law, and then some of the comparison between various transport phenomena of transport, like the momentum, energy, and the mass. So let us start first. We'll start with the previous questions, that is this. So the question is, like, how much positive and the negative charge is there in 25 ml cup of water. So we have to calculate the total charge that is present in a cup of water. Okay, so for that we'll go here and okay, so our question is, we have to calculate total charge in a cup of water. Okay, so it is the cup of water is volume is given as 525 ml. See, so here in order to solve this, we have to calculate the charge. We know that at every molecule or every atom, if we say like sort of if we consider every atom, so it has multitude of, it has different kinds of the charges. For example, it has electrons and it has protons. Okay, so protons. Okay, so if we consider a simple picture of an atom, using the Bohr's model of an atom, so what an atom consists of is actually a positive charged core, and there are shells around it which have negatively charged. Okay, so we have to similarly in case of a water molecule, if we say that we have one O, we have H, and we have H, thus we have an oxygen atom and we have an hydrogen atom. Both these, they have both electrons as well as protons, so we have to calculate the total charge of this. So now the we have given is the total volume is actually given. The volume is 525 ml. Now since we need to calculate the amount or the number of the water molecules, so we need to consider the density of the water. Okay, so we have to check what is the density given in the equation. Since there is no density, so we'll consider as density is density of the water to be considered as 1 gram per ml. Okay, now another thing is we need to know the molecular mass of water. Okay, so it is 18 grams. Okay, now how many number of molecules will be there in 1 mole of water? So it will be equivalent to that of the Avogadro's number, that is given by 6.023 into 10 to the power 23. So in any atom or in any molecule, in any substance, the number of the molecules that are contained in 1 mole will be equivalent to that of the Avogadro's number. Okay, now since we know the, now we have to calculate a number of moles of water in glass. Okay, so the total number of moles of water in the glass will be 525. If we consider the density as 1 gram, therefore the so before that we have to calculate mass of water in glass. Since we know that density is given by mass per unit volume, so the volume is given, so the mass is given by density by volume. As a result, mass will be given by so it is actually wrong, sorry, density multiplied by volume. Okay, so the mass will be, density is 1 gram per ml multiplied by 525 ml. So if we can say this and this cancels out, what we will get is 525 grams. Okay, now we have this much gas. Now we have to calculate the number of moles in glass, they will be equivalent to 525 grams divided by 18 grams. We cut this will be given by some quantity. Okay, we'll see. Then what we'll calculate is we'll calculate total number of molecules now. Okay, it will be equivalent to 525 divided by 18 number of moles multiplied by how many molecules will 1 mole contain, Avogadro's number. So I can write as number of moles multiplied by Avogadro's number. Okay, they will give the actual n. Okay, so if we calculate this, it will become equivalent to 175.67 into 10 to the power 23. So we have these many molecules. Now if we know that one water molecule, if we know that one H2O molecule, so it contains actually 2 hydrogen atoms and 1 oxygen atoms. Okay, now one hydrogen, what it contains? It contains 1 electron plus 1 proton. Similarly, 1 oxygen, right? So it contains 8 electrons plus 8 protons. Okay, so one water molecule will have total number of 10 electrons plus 10 protons. Okay, now what we'll do is since the total magnitude it has to be equal, because water is a neutral molecule, so we have to make sure that in S table the magnitude of positive charge is equivalent to magnitude of negative charge. Okay, now we have to know what is the magnitude of each charge. Be it positive or be it negative, it will be given by number of molecules, that means n, multiplied by 10 multiplied by what is the charge of electron or charge of proton. Okay, so if we calculate it, that will be equivalent to 175.67 into 10 to the power 23 multiplied by 10 multiplied by 1.6 into 10 to the power minus 19 coulomb. So the magnitude of each charge, if we write MC, either it will be positive or it will be negative, it will be given by 2.81 into 10 to the power 7 coulomb. Okay, so this is our final answer. Now this is the amount of the charge that is contained in the glass of the water that was actually given. Okay, so now this completes our first question. Now we will go to the question second. Okay, so if we see what is the answer, that is 2.81 into 10 to the power c, that is 2.81 into 10 to the power c, that is actually shown here. Okay, now the second is we have to assume an arrangement of charges in an xy plane 4 at 0 0 and 2 electrons at this and 2 electrons at 30 from the x-axis, and the distance of 130 from the origin, the total okay. So we have to calculate the total dipole moment. Okay, so we have to calculate the total dipole moment that is present in this arrangement. Okay, so we have to calculate. Okay, so for this what we'll do is, okay, we'll consider this as an xy plane. This is 0, 0. Okay, so we have to consider 4 electrons that are present at 0, 0. Then we have 2 electrons at 162. Okay, and then we have 2 electrons at an angle 30 from x-axis. We have 2 electrons here, so this angle is 30 degree. Okay, so we have to calculate the total dipole moment that is coming from this system. And the distance of 143 from the origin. So the distance from here to here is 143 picometers. Okay, so I'll use a simple trigonometric equation here. If we have, for example, we have an y-axis, we have an x-axis that is shown here. This is x-axis, this is y-axis. Since this angle is theta, is 90, if we want to calculate what is the x component, so x of this for example, I will write here a. Okay, so the x component of this will be equivalent to a cos of theta, and the y component will be a sine of theta. Okay, so we have to will use this to calculate the total dipole moment. Okay, now we know that dipole moment it arises because we have the two dipoles. For example, we represent this when this is positive charge and this is negative charge, for example. So the total dipole so the dipole moment of this arrangement will be equivalent to the magnitude of either charge, that is q, multiplied by what is the distance between them, for example, that is d. Now if we have a different arrangement of the atoms, what we have to do is we have to do the vector summation. Okay, so the magnitude of the all other this arrangement is summation over all the charges and summation over all the dipole moments. Okay, so okay, now we'll see this arrangement. Now if you see the distance of these 4 electrons from that of the 0 position, it is actually 0. Okay, so what we'll do is we have here 3, so the charge is 4 electrons multiplied by Ri is 0 for the 4 electrons that are present at the origin. Okay, plus then we have 2 electrons that are present at R2 distance, and then we have 2 electrons that are present at R3 distance. So this is, for example, this I consider R2 and this I consider R3. Okay, now what we have to do is okay, R3. Okay, now we this R is actually the distance from the center. Okay, this r is distance from the center. Now we know that for this okay, so we know that r1 was 0. Now we have to calculate r2. R2 is if we consider r2, we use the vector summation. So what it will vector notation, it will be I, where I is a unit vector across see. What we have to consider is that dipole moment is actually a vector quantity. So once it's a vector quantity, it has both magnitude as well as it has some direction. Okay, so if we calculate magnitude, we have to calculate direction. So the summation of all will be actually the vector summation of all the vector summation of all the dipole moments. Okay, now if we consider here that here r2 is a vector and r3 is a vector, similarly r1 is a vector and it is equivalent to 0. Now r2 is a vector. Now if we say that use a normal rotation, that a unit vector across x-axis is I unit vector, then along y-axis is j, and along z-axis or z-axis is k. Okay, so we write in this notation. So along this it will be I x2, where the magnitude is x2. Similarly for r3, what it is actually in the direction of both x as well as y. What we will write is r3 is equivalent to, it is component along x3 plus it is component along y3. So actually, since we know that r3 is here, this is r3, so what we are, it is component along this will be I x3, it is component along this will be j y3. Okay, this is x and this is y. Okay, so now so we have r3 is equivalent to x3 and y3. We know that x2 is the magnitude of r2, so that is directly that is equivalent to that of 162 picometers. Now that is given x2. Now what is x3? This x magnitude. X3, as I explained here, we can calculate it as the cosine component of the a. So it will be equivalent to r3, where r3 is given by this, if it is theta, r3 cos of theta. Okay, here we have r3 cos of 30 degree. Okay, so the value will be equivalent to 143 multiplied by 0.866. The value is equivalent to 124 picometer. Okay, now we have to calculate y3 also. That is equivalent to r3 sine of theta. R3 we know is 143 sine of 30. It will be equivalent to 143 multiplied by 0.5. That is given by 71.5 picometers. So if we go back to the diagram, from here up to here, for this component it will be 71.5 picometers that we have calculated. Okay, now we have to calculate the total dipole moment. Here we have to see that since a dipole moment is a vector quantity, and for example this is the dipole moment. So it will have an x component that is along the x-axis, and it will have a y component that is along the y-axis. Okay, so since we have the components both along this r is both along x direction as well as y direction, so we can calculate the dipole moment across x direction and across y direction. Okay, so if we calculate along the x direction vector summation, so all the x components will come in this. Since the vector summation of x components with y is 0, so as that means so it is 0, so there will be no component of distance along the x component along the x. So what we have to write is minus okay, so minus 2 electrons along the x2, then we have again minus 2 electrons x3. so this is the x2 corresponds to these 2 electrons. I shall individually color them. We have these okay, we have these 3. Okay, so these 3 we have. Now this is along the x component, this is which was on the charge that was present on x direction, and this is the charge component that was present in between the x and y. Now using the formalism we can calculate it is 2e multiplied by this 2e will take common x2 plus x3. Okay, this is electronic charge, we will write picometers. It will be given by minus 2 multiplied by, so x2 we know is 162 multiplied by what is x3, so x3 we have here 124. Sorry, this is plus. That is equivalent to minus e multiplied by 572 picometers. So since what we have done here is since we know that dipole moment is a vector quantity, so we have added separated the x components and the y components, and then combined the x components first. Now we'll combine the y components. So now what will be the y components equivalent to y component of dipole moment? It will be given by minus 2e, since we have only one y. Okay, so minus 2e, y3 we have calculated, y3 is 71. Okay, so we calculated x direction, and now we calculated mu across y direction. Now you might have seen that in case of a vector summation, what we have is total mu is given by mu x plus mu y plus mu z, not the in vector. Okay, but if we want to calculate the magnitude of mu, we can do mu x square plus mu y square plus mu z square. Okay, since here mu z is 0, so we can write magnitude of the mu will be equivalent to square of addition of square of both these two. Okay, so we have 572 multiplied by electron का square plus 143 electron का square now, and the whole will be under root. Okay, so if we put the value, we calculate what is the value of this, and we'll put the electron outside. Since I will solve E and E for both is out, then inside it will be 5 7 2 square plus 1 4 3 square. So it will be E, that is the electrical charge outside, and then 5 7 2 plus 1 4 3 square, and this whole will be under root. Now if we put in all the values, what we'll get is 9.45 into 10 to the power minus 29 coulomb meter. Okay, so that solves our, but since it is given in the dBi, so we have to convert this into dBi. So magnitude of the mu in dBi, I will write, will be equivalent to 9.45 multiplied by 1 minus 2 9 divided by how many dBi is in 1 coulomb centimeter. 30. So this is in coulomb meter. This thing is in dBi, no, coulomb meter by dBi. So what we'll do is this and this cancel, and the total value will be 28 dBi. So this is our answer. We have to see 28 will be the answer. Okay. Now let us take another question. Our next question is regarding the molar polarization of a substance varies inversely with temperature and is 75.74 per centimeter cube per mole at 320 Kelvin, and this at this. So here we have been given the change in molar polarization as a function of the temperature, and we have to calculate the dipole moment. Now if you if people remember in the last lecture, probably I can push it out. Yeah, so we have shown this. Yeah, so this is our polarization. So we have shown the difference, yes, so we have an orientation polarization that is given by mu square by 3RT. So we have to construct polarization, induced polarization and orientation polarization. Now we'll use this orientation polarization, and we'll calculate what is the dipole moment from, since we know that orientation polarization, it depends upon the temperature. Okay, yes, so we'll take it from here. Okay, so we have a question. Okay, so we have been given molar polarization, which is a function of temperature, and we have to calculate the dipole moment. Okay, so we have to calculate the dipole moment. Now if you see, and how the as in the last lecture I have shown that polarizability and dipole moment and molar polarization are related by, so I have used this equation. Molar polarization is Na by 3 epsilon naught. Okay, then we have KT, so this equation, so where Pm is molar polarizability, Na is Avogadro's number, E naught is permeability of free space. I have shown this equation in the here. If we see, if you people remember, have seen the last lecture, so I have shown that this part, it is actually composed of induced polarization, and this is orientation polarization. So the summation of both these will give us the total polarization. Okay, so this was the permeability of the space, and mu here gives the dipole moment. Okay, where T is the temperature. Now if we rearrange the above equation, what we will get is alpha plus mu square by 3 kT will be given by 3 epsilon naught Pm by Na. Okay, so we'll get this equation. We'll rearrange it further. What we'll do is we'll take mu divided by 3K. This temperature will take on the not this. What we'll do is actually, sorry, now if we say that we have a condition where when the temperature is T, at temperature T1, for example, our molar polarization is Pm. Okay, at temperature T2, our molar polarization changes to Pm dash, for example. Okay, then we can write this equation. That means mu square by 3K. Okay, then we have multiplied by 1 minus T divided by 1 minus T star, that is the T1 or T2, and on the other side 3 epsilon 0 by Na multiplied by Pm minus Pm star. Okay, so since we know that polarizability does not depends on temperature, this alpha. So it will be constant for both this as well as this. As a result, once we subtract equation 1 from equation 2, we'll get 0. Okay, so this will get neglected. As a result, we derived this equation, we get this equation. Okay, now if we do further rearrangement, we'll get this mu square that is actually here will be given by this 3 multiplied by 3 is 9 epsilon 0 this k. Okay, then multiplied by pm minus pm star divided by Avogadro's number multiplied by 1 by t minus 1 by t2. So this is our equation. Now if you see this we don't need. Yes, so we have been given the molar polarization at 2 temperatures. Okay, so we'll consider T as T1 and this as T2, and the molar polarization PM and PM dash, so that we can calculate the dipole moment. Okay, now using these the given equations, what we can calculate is mu square is equivalent to, okay, 9 multiplied by what is the value of E naught, that is 8.85 10 to the power minus 12 J per meter. Okay, then multiplied by, now we have PM minus PM star. So at T1 what was our molar polarization, that is this. Then we have sorry, this is the value of this is 9, and then we have epsilon, that is up to here. Then we have value of K, that is here, Boltzmann's constant. Okay, now we have PM minus P, so we will write 75.74 minus 71.43. okay, so these are the two parameters. Yes, so these are 75 at 3, these are the two parameters that are given. Okay, then we have divided by NA. NA is Avogadro's constant, and 1 by T1, 1 by T2. Okay, so calculating these values, what we'll get is 1.05 into 10 to the power minus 59 Coulomb square meter square. So that means mu will be equivalent to 3.23 into 10 to the power minus 30 Coulomb meter. Okay, because mu is the under root of this. Okay, so if we convert that into the device, what we'll get is 3.23 So one debye consists of 3.335 into 10 to the power minus 30 coulomb meter. Okay, this and this will go cancel. We calculate the total value, it will come 0.983 is the mean. So that is our value. So what we have used is, we have used the change in polarizability or molar polarizability as a function of temperature to calculate the dipole moment. Okay, so our value is 0.98968, that is 0.968 is our value. Okay, now we have another equation that is on dipole moment. Okay. Two oppositely charged ions are separated by a distance of 2.17 and the charge on each ion is 3.33 electrons. Calculate the dipole moment in device. So this is a simple question where we have two opposite charge orientation. That is what actually a dipole consists of. So what we have is, we have two oppositely charged, for example positive here, and then we have a negative here, and then they are separated by some distance. So the distance is given by 2.17 angstrom. The distance is 2.17 nanometer. The magnitude of each charge is 0.33 e. This will be minus 0.33 e. This will be plus. Okay, so simple question. We have to calculate the dipole moment. So we know that dipole moment mu is equivalent to magnitude of either charge multiplied by the distance, so that is the separation between them. Okay, here q is given by 0.33 electrons or electrical charge, and L is given by 2.17 nanometer. Therefore mu is given by Q into L, or Q into L, that is given by now we know the value of basic electrical charge. It is coulomb okay, so if we calculate this value, it will come 1.146 into 10 to the power minus 28 coulomb meter. But here the value has to be calculated in the device, so we'll know that how much one device contains. Coulomb meter. We'll cancel these two. We'll calculate the total value. Our mu will be given by 0.344 into 10 to the power 2 debye, or we can write 34.4 debye. That's our answer. A simple problem. So now we have another question. If the resultant dipole moment of two dipoles is 4.3 and the dipole moment of each dipole is this. So okay, so this is simple, since we know that we have a question. It is actually regarding the vector summation. Since we know that dipole moment is a vector quantity. Okay, so we have to if we know the resultant, we have to do the vector summation. For example, if we have two dipoles like dipole 1 and dipole 2 along this direction, this is mu1, this is mu2, the resultant dipole will be along this direction. Okay, so we'll simply do the vector summation. If we know that from your basic classes, the total magnitude of dipole moment will be given by mu1 square plus mu2 square plus twice mu1 mu2 cos of theta. Okay, so if this is mu total, this is mu1 mu2, and this theta is the angle between them. So what we have been given is actually, we have mu1 given, we have mu2 given. Okay, the mu1 is equivalent to 2.13, the mu2 is 3.12. what we have to calculate the theta. So simple vector summation will calculate theta. Now we also know what is mu t, that means total it is 4.3. now using the value 4.3 square is equivalent to 2.13 square plus 3.12 square plus 2 multiplied by mu1 multiplied by mu2 into cos of theta. So 18.49 will be given by okay. So calculating this total value, it will be 18.49 theta will be cos inverse of this quantity. This is around cos inverse 0.32. if we calculate that, it will become, theta is given by 71.34. so that is our answer, 71.34 is our answer. Okay, so this completes our assignment regarding the second assignment, that was regarding the polarization, polarizability, and polarization, polarizability, dipole moment, how the dipole moment changes as a function of temperature, and how we can calculate the dipole moment from how we can calculate the dipole moment from total dipole moment from all the dipoles that are that can be present inside a system. Okay, so this is done. Now what we can do is we will go to the assignment third. So the assignment third is mostly regarding the fluid dynamics. So fluids are those which can flow under some under a particular conditions. For example, liquids and gases are fluids. Okay. Whereas solid is a condensed, solid as well as liquid is a condensed phase. So yes, let us go to the uh, next assignment, that is so this one will close. So we have a PPT open somewhere, not, yes. Okay, zoom. Okay, so this is the third, actually we have started the third session. Okay, so today we'll try to see how many questions we can solve from these. So this is like these are regarding the thermal conductance, thermal conductivity, mostly that are related to the dynamics of heat, like thermodynamics, the mass transfer and other things. Okay, so if we see the first question, if a molecular diameter of carbon monoxide is 420 meters, what will be the coefficient of thermal conductivity at 3.2 atmosphere? So here we have been told to calculate the thermal conductivity when okay, so we have been told to calculate the thermal conductivity as a function of temperature. Thermal conductivity we have been told, and the molecular diameter is given. Okay, so I'll give a brief introduction about different processes that can happen at like heat transfer. From that we'll get the equation and we'll try to solve those questions. Okay, now the first that I'm talking about will be the heat transfer. So for example, the heat transfer is actually the transfer of heat or sort of a thermal energy from the high temperature to the low temperature. Now what heat transfer is actually, it changes the internal energy for both the systems, and it is in accordance with the first law of thermodynamics. So if we see the first law of the thermodynamics is that the energy always transfers from higher temperature to that of the lower temperature. Okay, so if we see that this heat transfer actually we are using, and it's happening every day, and we are using like in different heat engines, our sensors, thermal sensors, everything they works on the heat transfer. Okay, so if we see that if we take, for example, I might have shown, no, probably not here. Okay, heat transfer. Okay, now if we see that heat transfer, where we use it, like you see that we use this heat transfer as in heat engines. Okay, and here the heat in heat engines, or in every engine, you might have seen like an ideal Carnot's engine, the heat always transfers from a higher temperature to that of the lower temperature. Okay, to the cold area. Heat transfer always from the lower to the cold. For example, this different examples of the heat transfer are like first I'll see the different mechanisms. Now the heat has to transfer, that means the thermal energy has to transfer from that of the cold side to that of the hot side. Now it can happen through different mechanisms. The first is called as a conduction. In case of conduction, there is no actual transfer of the mass remains constant. Okay, so no mass gets transferred from hot to the cold region. Okay, but only the energy gets transferred. So this is the conduction. Okay, then there is convection. In case of a convection, there is actual mass transfer. So in convection, what will happen is that if we take a hot side and if we take a cold side, now from the hot side some of the particles will move towards the cold side. This is the cold, this is T1 and this is 2. So for example, if T1 is, now what will happen is that the mass of this, some particles will move from here to here and they will carry, since this particle they are at higher temperature, so internal energy depends on temperature, so the internal energy will be higher. As a result of, once they move from hot to the colder side, they'll take that energy with you, so the heat transfer will occur. Okay, the third is the radiation. Radiation is through the electromagnetic waves in or in which is through the electromagnetic waves. What will happen is every if you see the black body radiation, any body or any object which is present at any temperature, it will give radiations out. Okay, so these radiations like what will be the magnitude of those radiations, I'll explain it probably. So here we are talking about the heat transfer. Okay, so we have known that the mechanism of the heat transfer is conduction. Okay, the second is convection and the third is radiation. Okay, so if we'll make if the red represents that higher temperature, so what we'll do is we'll make a, for example, this is our body or this is any body, and on this side there is higher temperature, so as a result the particles are present at higher temperature. On this side will represent lower temperature. So no matter what happens, the energy will always this is T1 and this is T2. Okay, if T1 is greater than T2, then what will happen is the heat transfer will happen. There is heat transfer. Okay, so I have explained the conduction, convection. Now there is a radiation. Now you see at any object, it evolves, it gives radiations at any particular temperature. For example, if you see any object that has a temperature T, it will give some radiations which are a function of the T, whose profile is a function of T. Now that profile is given by the you might have seen the Rayleigh-Jeans law or the Wien's law or this Planck's radiation law. So what we can see is the energy intensity that is given by it actually depends upon the so if this is lambda, this is increasing, so here now if we consider any T1, T2, T3, now this is a particular body which is present at T1, T2 or the T2, and this is the radiation profile, and at each time it gives the amount of the radiations or the power density of the radiations in that particular lambda. Now at different temperatures the heat the radiations are given, and the profile of those radiation type of variations are given. They are directly they can be quantified by Planck's radiation law. Okay, so this was actually the first phenomena that was seen, which does not explain which was not explained by the classical principles. Then the Planck came and then he explained this on the basis of the quantum mechanical properties. Okay, so what I want to say here is the heat can be given in the form of radiation, and the third type of that is shown here, or we can say it is within the three, is vaporization. So in the vaporization, what will happen is the vapors will come out. Now, like for example, we put a heat like water and we heat it to some, then what will happen is the vapors those vapors will have higher energy. Okay, now because of that, those vapors are going away from the heat, they will take some heat with them or the internal energy with them. As a result, this will increase, the heat transfer will happen. Now this heat transfer, what we use, this is in heat engines, we use this in heating, we use in cooling, refrigerators, AC, like everywhere heat transfer is used. Now some common examples that we see heat transfer is like, just like if we body is cooling, if we put water on the body, cold water, our body feels like, because we have the temperature, like sort of temperature sensors over our body, our skin, our epithelial tissue, it can the dermis tissue, it can determine or sense the coldness in the temperature. And similarly we have home heating energy systems, they all work on heating. And some of the big examples are the greenhouse effects, where the greenhouse gases, they trap the infrared radiations that are coming from the earth. As a result, it is increasing and we have a radiation cooling. Okay, now first mechanism is the heat conduction. Okay, now you see, in case of heat conduction, what is happening is in case of a conduction, the heat is actually getting transferred because of the molecular vibrations within the material, but there is no actual motion of the material. For example, if we take in a conduction, we'll take solid rod. So we have a solid rod like iron. Okay, on in iron, on one side what we'll do is we'll heat it. Okay, so this side will get hot, this side will get cold. Okay, so here the temperature of T1 will be greater than T. What will happen is that there will be heat conduction from this, and we see that metals are very highly thermal conductivity. So what will happen is that this heat transfer will happen. Because of that heat transfer, now in this heat transfer, the iron particles or the iron atoms, they don't actually move, but actually only the heat moves. So this is called as conduction, for as I have shown here. So how it happens is that you see, when we heat, when we have a for example a conductor or any substance and we heat it, what will happen is that the molecules or the entities that make it, what will happen is they will agitate more and more. At higher temperatures they will agitate more and more. So because of that agitation, the molecules which are very near to the closed end, they'll strike to those molecules which have less agitation. Okay, now because of that agitation there will be collision. That collision will lead to energy transfer. Okay, so similarly this process happens till the whole energy is transferred. Okay, now if we see that what is the heat transfer. Okay, what we'll try to quantify the heat transfer. Okay, so if we see that say that T hot is the temperature on the hot side and T cold is the temperature of the cold side. As a result, there will be a heat transfer by conduction. Then what we can quantify it is, if Q is the amount of the heat that is transferred from a hot side to the cold side, and T is the total time that is actually taken for that, then the Q by T will be given by, it will be directly proportional to the surface area of the contact. Now if you have more contact, you will have more heat transfer. Okay, now and then it will be proportional to the what is the temperature difference between these two, T hot to the T cold, so delta T. So more the energy gradient, more will be the heat transfer. Then D, where D is the thickness of the barrier. If the barrier is very thick, then you will get less heat transfer. Okay, so where now if we remove this proportional, you will have a constant of proportionality called as kappa, where kappa is called as the thermal conductivity of a barrier. It depends on the material, it's a material property. Okay, so transfer of heat as a function of the time is the property of thermal conductivity, that is the nature of a material. Cross section inversely proportional to the barrier, and directly proportional to the temperature gradient. More the temperature gradient, more will be the heat transfer. Okay, now we'll go to the second. That is the convection. Okay, so as I told you that in convection there is an actual mass transfer. Okay, so convection is the heat transfer which occurs because of the mass motion of the fluid, such as air and water. For example, if you will take hot air from here and cold air from here, what will happen is the hot air particles will go from here, hot side to that of the cold side. So there will be mass transfer. Because of that mass transfer, there will be heat transfer. Okay, so why it actually happens is, once we are heating it, we are increasing the vibrations. Okay, we are increasing the kinetic energy. So the kinetic energy of the, if we know from the kinetic theory of the gases, that mv is equivalent to 1 by 3 kt. So kt, T temperature means more kinetic energy. Because we are increasing the kinetic energy, they will move more and more, so they will go towards the colder side. Okay, so this is called as this convection actually occurs on the hot surface because the hot air expands. That I know that, because once we are increasing the agitation, what will happen is it will expand. Okay, it becomes less dense. That we know, because once they have a more motion, it will have less dense. As a result, the hot air is actually lighter as compared to the cold air. And then now we see that now I have shown here like how a particular heater works. Now you see, if we have a heater, so inside the heater what will have is it will have some electrical element, light, that gives energy out in the form of radiation, or in the form of conduction. Now because of that, the air molecules nearby it, they will get heated up. Because that heats up, what will happen, there will be a warm air. That warm air will actually because it has more kinetic energy, it will move. Once it will move towards the here, there will be a colder air. Now here what will happen is a concentration gradient will be created. It will be less dense here, more dense here, or more dense here. Then what will happen is this mass transfer will occur from the colder to the hot side. Okay, now these cold particles will get heated up, and then this circle continues. Okay, so this is how a particular heater works, because of the heat conduction. So similarly, this mass transfer can be seen in my sorry, 1 minute. Okay, so because of this it can lead to a variety of phenomena that we see in our day-to-day life. For example, one of the phenomena is you see in if you take a pan and you put some liquid inside it, what will happen is that there will be a this flame will actually heat up the. So in this phenomena, we'll see that there is both conduction as well as a convection that takes place. Okay, if we see that now we heat this pan on the below side, since the pan particles or the iron particles, whatsoever the pan is made of, it cannot move, right? So what will happen is the heat transfer occurs by conduction. Okay, now because to the nearest liquid phase. Okay, now what will happen is that liquid phase, it got heated up, so because of that it becomes lighter, and then it moves up. Now once it moves up, there what will happen is the colder will move down. As a result, it will create convections. Okay, now these convections you can see when the liquid is boiling, or you can see these convections are responsible for air currents. Okay, the wind and other things, they are responsible for that. So this is the convection. Similarly, if you see if we put a cooking oil in the pot, like you put a cooking oil, and then what actually happens is that since we are heating the oil, so what will happen is there will be a change in the refractive index. Because of the change in the refractive index, since the optics depends upon the bending of light, depends upon the refractive index, so what will happen is that we can see that those convection currents that are actually happening. Okay, in a cooking oil. Okay, similarly convection is thought to be this heat transfer by mass transfer. It is thought to be of very important it plays a very important role in transporting energy from the center of the sun to the surface. So actually the reaction is happening at the center of the sun. Okay, then in order to transfer the heat, it is thought to be that the transfer of the heat from the center to the surface of the sun, it occurs by the convection. Now as I have written here, that convection is thought to play a very important role in transporting energy from the center of the sun to the surface, and in movements of the hot magma beneath the surface of the earth. So we have a hot magma that's inside the mantle or the core. Now there the energy transfer occurs by this. The visible surface of the sun photosphere has a granular appearance with typical dimensions of granules between 100 kilometers. The image, you see the image that is on the on this side, this was actually taken from the solar physics website, NASA solar physics website, using telescope. They see that you see there are different granules. These granules, now these are actually the convection cells, just like we see in the oil. They transport the heat from the interior of the sun to that of the surface. Okay, so the convection is very important in our day-to-day life. Okay, now we have shown the heat transport. Now as I have shown here, that it depends upon the thermal conductivity, this kappa thermal conductivity. Okay, now we'll have something, what is the thermal conductivity. As I have already told that heat transfer, when there is no mass transfer, that is called as a conduction. It does not occur because there is no motion inside the particles. There is no net motion inside the material. Okay, this rate of the transfer, it depends upon d, and it depends upon the contact size, it depends upon the barrier for the heat transfer, and also it depends upon the thermal conductivity, that depends upon the material. Now this material is this quantifying the thermal conductivity of different materials is very important. Okay, because you see, when we are using electronics, the CPU and other electronic components, they get heated because of the Joule's heating. Okay, now because of the Joule's heating, which is given by I square RT, they get heated up. Now if you go on increasing the heat, what will happen is that our electronics, the resistance increases. Okay, so what will happen is that the electrons will not function properly. So in order for that to heat, what we use is we use different coolers, CPU coolers and everything. Now there should be an efficient heat transfer from the electronic components to that of the outside. Thus we have to use some material that has very high thermal conductivity. In other cases, for example, in case of winters, like clothes and everything we are using, we need or in thermos flasks, where we want to preserve the heat or preserve the coldness. What we want a thermal conductivity that is very low. Okay, now because of the low thermal conductivity, we will have anything that is present in a tiffin or a thermos flask, it will remain, the temperature will remain constant for a longer period of time. So this is a very important to quantify, to characterize the thermal conductivity of the different materials. Okay, so as I have told you already, the heat depends upon the gradient T1 and T2. It depends upon area of contact, and it depends upon the distance between the two. Okay, so this is how the heat conduction is actually happening. So a molecule which is present at higher temperature, it has very high thermal energy. As a result, because of high thermal energy, as per the kinetic theory of the gases, it has higher velocity. Okay, now because of that higher velocity, when it move, it will strike here. Okay, now this strike will happen is that there will be another molecule or another entity that has lower energy. Once it strikes, there will be an energy transfer. Now this will go heat up. So similarly, other molecules, this number of collisions will happen, which transfer the heat. Now different materials have different thermal conductivity. Okay, now it depends upon the nature of the materials. Okay, now if we see that in case of gas, okay, the heat gets transferred by direct collisions, like one gas molecule transfers heat to the another collisions. Okay, okay, then as a result, because there is actual movement of the molecules, the thermal conductivity is low. That means the air thermal conductivity is low as compared to that of the metal, like iron. Okay, so the thermal conductivity is low, mostly in case of the solids. Okay, gases have very low thermal conductivity as compared to the majority of the solids. Okay, if we see that in case of non-metallic metallic solids, Okay, and the heat is actually transferred from one side to the another side by lattice vibration. So we have a particular structure of a solid. So at every point is where they are called as a lattice point is there are atoms or entities. So what will happen is once we heat up, what will happen is that these lattice pointers will start vibrating. Okay, now once they will start vibrating, this energy transfers from we call them as phonons. Okay, these phonons are energy carrying vibrations. Okay, these phonons go from higher temperature side to that of the lower temperature side. Okay, phonon. So as a result we get the heat transfer. Okay, and there is no net transfer of a material, just like in case of solids. Okay, just like in case of the gases. Okay, as a result, so this collective motion of this lattice vibrations, they are called as a phonons, or they are called as quanta lattice vibrations. Metals are having very high thermal conductivity. Okay, see, different heat transfer in different substances is through different mechanisms. Okay, so if we see in case of the metals, they have very high thermal conductivity. Why? Because the highly energetic electrons, because the electrons are mobile, right? Metals have a band, metals have don't have band gap. Okay, the electrons are mobile. So once you heat one side, what will happen is these electrons will gain large enough energy, so they will go from hotter side to colder side. Okay, so that is called as as a result their electrical conductance, their thermal conductivity that occurs because of the electrons, it's very high. Okay, so as I told, that metallic conductors have very high thermal conductance because the electron transfer. Then we have solids. The electron transfer occurs because of in solids, the electron transfer occurs because of lattice vibrations, also called as the phonons. And in gases, the electron transfer occurs directly through the molecular transfer, mostly and collisions. Okay, so this is in case of the, as a result, because of these differences in the mechanism, we will have a wide range of materials with different thermal conductivities. Okay, so thermal conductivity is a material dependent process, as I have shown already, that the total amount of the heat that can be transferred from one side to that of another side of a material depends upon the temperature gradient. Higher the temperature gradient, higher is the heat area of the contact. Higher is the area of the contact, higher will be the heat transfer, and is inversely proportional to the and is inversely proportional to the sorry, 1 minute, and is inversely proportional to the distance between the hotter and the colder side. Okay, so so now we are so yeah, so we have it also depends upon the material properties. That material properties is quantified by a parameter called as a thermal conductivity. Okay, so in this so we see this thermal conductivity is this kappa. Okay, now we should always know that here the negative is occurring because the heat will always transfer from hotter side to the colder side. So this delta T will be always from always negative. So in order to make this quantity positive, we have to write negative. Okay, so now if we consider ideal gases. Okay, the ideal gases are the gases which follow an ideal behavior, which follows all sort of, I will say, will follow the ideal gas equation. Now in case of an ideal gases, it has been quantified that so in case of ideal gases, we can determine the thermal conductivity. Now for ideal gases, the thermal conductivity is given. It depends upon the number of particles, obviously the number density, mean particle speed, okay, mean free path, molar heat capacity, and the Avogadro's number. So this is valid for ideal gases, okay. So this has been derived using the kinetic theory of the gases. Now for non-metallic solids, the heat transfer is like through the vibrations that we have already explained. It occurs because of the phononic vibrations. Now the phononic vibrations are actually sort of lattice vibrations, okay, where all the lattice particles they vibrate in coherence manner, okay. As a result, this lead to thermal current. Now we have seen that in case of the metals, they show an important character, that is they follow the Widman-Franz law. You see that in case of the metals, they have two properties are there. One is called as an electrical conductance, second is called as a thermal conductance. Now in metals, if we see, both the electrical as well as the thermal conductance, it occurs because of electrons. Now because of the electrons, we see the thermal conductance, and because of the electrons, we see the very high electrical conductance as well. Now Widman-Franz law, the thermal now we know that in case of the metals, the thermal conductivity is very high, okay, and they are also the best electrical conductors, okay. Now according to the Widman-Franz law, at a particular temperature, the thermal and the electrical conductivity of a metals of the thermal and the electrical conductivity, they are proportional to each other, okay, at a particular temperature. That means if sigma is the electrical conductivity, electrical conductivity is like, if we know that in case of a metal, resistance is given by is directly proportional to the length, inversely proportional to the area. So then what we can do is, I will probably write here, okay. So in case of metals, we are explaining Widman-Franz law, okay. So what Widman-Franz law says that the thermal conductivity in case of material is directly proportional to that of an electrical conductivity at a particular temperature. So if we know that electrical conductivity, this conductivity, I'll know, if we know that resistance of a metal is directly proportional to length and inversely proportional to the area. So if we remove the constant of proportionality, we'll have something this that is called as a resistivity L by A, okay. Now the if we put this resistivity is, this is given by, we'll just inverse the resistivity here, and then A so this is resistance, this is while this is resistivity. Now it does not depends upon the dimensions, it depends upon the material. Now if we do 1 by R, inverse everything is equivalent to 1 by this multiplied by A by L, where 1 by R is, this is called as a conductance, is equivalent to conductivity A by L. So the conductivity is given by conductance multiplied by L by A. So according to the Widman-Franz law, at any particular temperature, the thermal conductance is directly proportional to the electrical conductance. So if we remove the constant of proportionality, we can write thermal conductance by electrical conductance is equivalent to L multiplied by T, where T is the temperature and L is called as a Lorentz number, okay. Lorentz number for a majority of the metals is almost constant. So this is actually followed by metals, okay. Now recently it has been seen that this Widman-Franz law is actually also applicable in at quantum scale, where the conduction is quantized, like in case of conduction through the single molecules, okay. So then I'll explain more about the mean free path. Okay, now if we see that in case of kinetic theory of the gases, how it explains. So according to the kinetic theory of the gases, what actually happens is the molecules are actually vibrating all over. Okay, so what will happen is that one of the molecules it's going from all over, so the direction is all over. Then what will happen is that one gas molecule, or even in case of metal, is the electron movement. Okay, so the one molecule will actually collide with another molecule. Okay, then what will happen is its velocity decreases, then it goes from through a particular distance to while it attracts another molecule, another gas particle. So there is a distance and time lag between two consecutive collisions. That distance that is traveled by an electron or by gas molecule inside a gas is called as a mean free path. Okay, it is the actual or average distance that a gas molecule travels from one collision to that of another collision, and it is estimated from the kinetic theory of the gases by just a visualization. Okay, now if we see that a molecule has a diameter d. Okay, so the molecule has a diameter, as I have shown here. The molecule has a diameter d. Now this molecule will be moving towards this direction, and then once it strikes, it will be moving now it will be moving in this direction. Now if we see that so this is a molecule that is coming, so we'll see that it will strike with other molecule only and only if the path that is traversed by this molecule, it is being cut, or the another molecule is in the path of this molecule, gas molecule. Okay, now we want to calculate that path, so that is called as an effective collision area. Now you see this is our gas molecule. Okay, if any gas molecule that has even a small edge in this area from here to here, even a small edge, now this gas molecule will strike it. There can be head-to-head collisions and there can be side-side collisions. Okay, so that means any molecule that comes within the range of this d, from the center of this, it will get collided with this. So that means the total effective area of the collision will be the area of this circle where d is the diameter of the molecule. This is called as an pi d square. This is called as collision area or an effective collision area. Okay, so any molecule that is coming within this range of a particular molecule, they will get collided to each other. So this is a molecule that is actually shown, and the effective collision area is this. Okay, now if we use now that means any when a gas molecule is actually moving, any molecule that is coming within this area will get collided with this gas molecule. Okay, so if we know the number of the molecules that are present in that area, now okay, so we'll approach it this way. Now we know this area is, now this gas molecule will also have some velocity. So in a particular time, this gas molecule will move from here to here. Once it moves from here to here in particular time, for example t, what will happen is that it will sweep a volume, this area. Now if there are gas molecules within that volume, they will cause a collision with this molecule. Okay, so this is the total effective volume of this gas molecule where the collision will happen. Okay, now we can determine how many number of the molecules are present in this volume if we know the number density, number of the particles per unit volume. We know the volume that is swept by a gas molecule while traversing, so we can calculate the now we see that if we consider diameter as 2d, this is the area. Okay, this is the molecule size. Now if for example in particular time t, the molecules swept from L distance. Okay, from L to L. The molecule is actually moving through a distance for a time t. For time t, the molecule sweeps L. So what will be the velocity? It will be L by t, right? Then what will be the volume? It will be cross section, that means pi d square multiplied by L. Since that means pi d square v t. So this will tell us the effective volume that is swept by a molecule, and if there is any molecules that are any other molecules that are present in that volume, what will happen is the collision will happen. Okay, now we know that now what will be the mean free path. Mean free path is now we have to calculate the mean free path. That means the distance that is traveled by a gas molecule between from one collision to that of another collision. Now we know that the volume that is swept by the gas molecule in particular time t is this much. Okay, if we know the number of the molecules per unit volume, it means what it will tell us. It will tell us if we know the number of the molecules per unit volume, okay, it will tell us number of the collisions that has happened. Okay, so we take the swept volume multiplied by number density. Okay, that will tell number of the molecules that are present in this volume and equivalent to the number of the collisions. Okay, so what we'll do is we'll say the number of collisions will be the volume that is swept by the gas molecule in time t multiplied by the number density. Number density is number of the molecules per unit volume, so it will tell us number of the collisions. Now we know that the number of the collisions. Okay, if we can see that what is the, if for time t a particular gas molecule has swept, or the distance traveled by a particular gas molecule is d. Okay, so what will be this velocity? Velocity will be d by t. Okay, so if the distance traveled is d and the number of the collision is given by this, so if we divide d by number of collisions, we'll know the mean free path. That means the distance between two consecutive collisions. So that is what is given here, where vt is, this is called as a velocity of the gas, this is the time t, this is the volume of the interaction, and this is the number density. If we cancel this and this, we'll calculate the mean distance that is traveled by a gas molecule between two collisions. So this is called as a mean free path. Okay, here we see that here what we have used is the average velocity. Okay, average velocity, velocity of the molecule. Average velocity means, you see, when what we have considered is, we have considered that once a gas molecule moves, the other gas molecules are at constant, they are not moving. But the issue with this is the other gas molecules are also moving. So we don't have to consider the absolute velocity of a particular gas molecule, we have to consider the relative velocity. Okay, it depends on, because if for example a gas molecule is swept and another gas molecule is in the way and that is also moving, then the number of collision, everything will change. So what we have to use, use the concept of relative velocity. Okay, so relative velocity is will tell us the distance. Relative velocity, when we put in this equation, we will get a real mean free path estimate from the kinetic theory of the gases. Okay, so that we will call it as a refinement of the mean free path. Now what is in the refinement? What we'll do is, here we have taken the velocity of a particular gas molecule. Now the problem with this is that this velocity, this number of the collisions will change as a function of relative velocity. So because other gas molecules are also moving, so we cannot use the absolute value, but what we have to do is we have to use the relative velocities of these two. For that we'll do the refinement of mean free path. That we'll do in the next lecture. Okay, so briefly I'll revise. So what we have done is we have solved some of the questions from the previous assignments. Okay, then I have given the introduction about the heat transfer, what are the different mechanisms of the heat transfer, and how it works, and what are the different examples for the heat transfer. Okay, now different mechanisms I have explained. The heat conduction, I have explained the convection, and I have explained a little bit about the radiation as well. Okay, a little bit about the radiation as well. Then I have shown the how different material, why different materials have different heat conduction by quantifying a value called as a thermal conductivity. Okay, different materials have different thermal conductivity depending upon the mechanism of the heat transfer in those materials. Okay, so we have concluded that, and we have seen particular examples why this heat convection is happening and what is its impact on our day-to-day life. Then we have seen why different materials have different conductivity. The solids have the highest thermal conductivity because of the electronic movements. Okay, and the insulators, other solid materials have the thermal conduction is happening because of the phonons. Okay, the lattice vibrations, in phase lattice vibrations. And then in case of the gases, it is happening because of the movement of the gas particles. Okay, then I have seen a particular case, that is because the solids have high thermal conductivity, high electronic conduction. We have seen a relation in solids, that is the Widman-Franz law. Now I have told you that Widman-Franz law is has also been seen to be applicable in quantum systems, where the conduction is quantized. Right, so for example, in case of the single metal contacts or molecular junctions, where it has been seen. Okay, so then what I have shown is I have shown the concept of the mean free path. How we can calculate the concept of the mean free path by using a simple visualization, this visualization approach called as a surveys approach. Okay, this surveys approach gave us the mean free path, but here we have considered the velocity of one of the gas molecule. But since all the gas molecules are moving, we have to use the relative velocity here. Okay, that we'll do in the next lecture, that is the refinement of the mean free path, and we'll also explain some other like mean free path and its relation with the thermal conductance dipole moment. Then what is the average velocity, how we can calculate. Then diffusion, rate of the diffusion, it is equations. Then mean square displacement in a particular molecule and how it is related to a diffusion coefficient and diffusion flux. We have different types of the flows, laminar flow, viscosity, and what is the relation of the viscosity with various parameters. Then we have the Stokes law, and then we have a different physical men. On the basis of this, we'll explain, we'll try to solve this. Now from these concepts, we have these derivations or these equations. From these equations, we'll solve the these questions in the next in the next PMRF session. Okay, next TA session. So thank you so much. If you have any questions, you can post or mail me, then accordingly we'll take in the next session. Thank you so much. Goodbye, good evening.